we're going to start there. We'll start there. All right, how about we work? What do you think? Yeah, it's time. Okay. Oh, I wanted to start by, addressing exam 5 briefly. First of all, to apologize for not getting the topics list up for either exam 4 or exam 5, but I'll do that as soon as I can. Suffice to say that we are considering this to be the MP5 exam. And in addition, we were thinking that that LabDict would be a good source of problems. So those are kind of the things you want to focus on. We're probably not going to emphasize AVL trees in this exam because the lab this week contains some of the implementations from AVL trees, and we want you to be able to, have that well behind you before we actually test you on it. So those are likely to be in the next exam. All right, and I'll try and put that information online so that you have it to refer to again. Are there any other questions or administrative issues that I know, I'll ask for you. Hey, Cinda, what's the status with grading? Oh, hey, I don't know yet. We'll be working on it. So, this is the persistent issue of our day in the context of this course, is to get all the grades back to you so you know how things are going. And again, I apologize and ask you to bear with us. We understand that we are behind the ball here. Okay, any other questions? So yes, grading, check. I felt guilty about it. Any other questions, issues? Things are okay? I counted last night. I think we have 16 lectures left. What I don't remember is whether that counts today. And my just did a little because it's really 16 lectures left at all. All right, so we were talking about AVL trees. Oh yeah, look, lecture helper is going. We're trying to collect data. So it would be great if you use this, okay? It looks like this, lecture helper. .cs.illinois.edu. And we'd love to see you there. I'll be looking, and I'm trying to do better at it every time. Okay, so we were talking about AVL trees, and those were in the context of a brighter, spankier, new binary search tree. So they were a better implementation of a binary search tree. And binary search trees were introduced to you in the context of the dictionary abstract data type. So our analysis of AVL trees is really simultaneously an analysis of our best guess at running times for, or best guess at an efficient implementation for, the dictionary abstract data type. So what we observed is that the running times for binary search tree-based algorithms at all were proportional to the height of the structure, okay? Now, I want to spend a couple minutes investigating whether or not we believe that to be true in the context of AVL trees. So we're going to look at this applet one more time, or this application one more time. And then we're going to argue that, in fact, AVL trees do satisfy the height requirement that we like. Okay, so suppose I bring to you a binary search, suppose I bring to you an AVL tree, okay? Here it is, it's this mythological AVL tree. Here it is, oh, I can do one. There, I brought you an AVL tree, okay? Here it is. Now, this is a particular example of one. I want to know in general what you would like to say about the height of this thing. What would constitute good news with respect to the height of an AVL tree? Yeah, that's the definition of it, that the height differences are less than or equal to 1. But overall, what's the height of an AVL tree? What's the height of it? I'm not asking this the right way. All right. Rewind. Let me start over. I'm going to make a binary tree out of n nodes. Now my question is, what's the very best binary tree I can make out of n nodes, n vertices? What's the very best? What's the height of the very best binary tree I can make out of n nodes? Log base 2 of n, right? Big O of log base 2 of n, right? Okay, so if I come to you and say, here's an AVL tree that I promise you has constant height, you go, no way, it's a binary tree. The best you can do for the height of a binary tree is log n, okay? So you don't believe me if I say it's better than that. Now, if I say that this is just, this is just a binary search tree, how tall is it? How tall is a binary search tree in general? It's not a special binary search tree, just a plain old binary search tree. How tall is it in the worst case? What's the worst looking binary search tree you can think of? N, right? It's tall. It's very tall. Now, we are going to make an argument about the height of AVL trees. The very best news we can hope for is that they are logarithmic in height. The worst news would be if they are linear in height. So our argument today is going to be that our AVL trees are, in fact, logarithmic in height. Now, I look at that tree and I go, it's kind of short, but it is actually as short as it can possibly be for that many nodes, right? It's as short as it could possibly be for that many nodes. Oh, that's interesting. Okay, I'm going to make you one that is not as short as it can possibly be for the number of nodes it contains, okay? Let's try it. I'm going to add a 35. Uh-oh. Am I going to get a rotation when I add 35? Will I get a rotation? No. Why didn't it add? Insert. Oh, it was just slow. Oh. Okay. All right, so I added a vertex, but I didn't change the height. Now I'm going to add one that will change the height, okay? This one is going to be What? 70. Go. Insert 70. Okay. Comparing. Yeah? No. Aren't you glad you came to class today? That's supposed to be self-effacing humor, not truth. Okay. Oh, did I create something that was out of balance? Oh my gosh. Life add 75. Is this as short as it could be with that many nodes? Yes. Okay, can I add a vertex without making a rotation? What is it? What number could I add? What key could I add that would not create a rotation? Yeah, I was going to add 71, but I'll do 76. I think that will, no, I'm sorry, that will change the height, but will not create a rotation. So we'll change the height of the tree, the overall tree, but will not induce a rotation. Okay, so 66, I believe we'll do it. Let's try it. So, go. I'll speed it up a little bit. Sorry. So where does 66 go? Make sure you see where 66 goes. Okay, it's going to go here. Now the tree is taller, but no rotation is required, right? And I assert that there is actually a shorter tree, right? So this tree is an ABL tree. No rotations were required. It's maintained as an ABL tree. Each one of them is, each node is the root of a height-balanced tree. And yet, it's not as short as it could be. It's taller than logarithmic, right? Because I could certainly take this last vertex, which is farthest from the root, and tuck it up someplace else. So this is, for that set of keys, not the shortest tree we could build. So ABL trees feel a little bit shorter. They feel like, well, we're kind of adjusting heights in such a way to keep them close, but we cannot yet necessarily argue that they are as short as possible because they are not complete trees or perfect trees or even trees that, that don't have gaps in the levels above the lowest level. Okay, so how tall are ABL trees? Now, algorithms for inserting and removing from this structure, I argue, are proportional to the height. Let's just take insert as an example. The act of inserting means you go to the bottom of the tree, just like you do for binary search trees, and then, critically, you do a little bit of work, possibly all the way up the tree again, as you emerge from your recursive calls. Now, if that amount of work at every stage is a constant amount of work, then asymptotically it costs you no more time than it took you to get to the bottom of the tree to begin with. That is, the running time of rebalancing the tree on the way up is still proportional to the height of the tree to begin with, okay? Does that make sense? That was a lot of verbiage. I realize it was a lot of verbiage. I'm going to do one more insertion into the structure just to be able to talk aloud that same explanation again. All right, so I want an insertion that will induce some kind of rotation. You figure it out. You tell me when. I need an insertion that will induce a rotation. 40 will do it. Yep. All right. So if I insert 40 into this structure, first of all, what kind of rotation will happen? A left rotation about what key? 33 is correct. Okay. Let's see if that happens. Ready? Okay, so we're going down, and right now you have no idea whether we're inserting into an AVL tree or just a plain old binary search tree. It's now that it becomes salient. Right now we're checking balance. Oh, look, there's an imbalance, constant amount of work to rebalance, and then we continue our way up the tree. Okay? So the act of rebalancing is still just something that happens in the course of navigating up the tree as you emerge from the recursion. Okay? So it's still the same. All right. So I'm going to go back to this, to our slides, which are here. And we're going to put all this into words, or into math. Okay, so running times for our dictionary functions. Running time for our dictionary functions are proportional to the height. We're going to argue that the height is big O of log n. Not exactly log n, but big O of log n, which gives us this constant factor fudge space. Okay, I need from you the definition of big O, and I'll start you off. A function f of n, which we're going to consider to be the running time of our algorithm, is big O of g of n, if and only if, what comes next? What comes next? Do you remember? Raise your hand. So I want you to kind of sketch it down if you know it, and let me know if that was the next character you wrote. Anybody write it? If there exist constants, and I like to write the fact that they are constants so that we remember they are not parameters to the problem. C and K, both of which happen to be greater than 0, but I'm not going to clutter it up by saying that, so that f of n is less than or equal to a constant times g of n anytime, that is when, n is greater than k. Okay? All right, boy, that feels like flashcard memory, right? Like that feels like, oh, I had to memorize that for 173. What I think is way, way, way more interesting is if you have to draw a picture of it so that you realize what it is you were arguing when you used this definition, okay? All right, so I'm going to draw a picture to communicate this. And because the function that we want to argue about is log of n, I'm going to draw my pictures as if they are log of n, kind of, okay? So here's f of n. I'm going to say that this is f of n. This is n, and this is the height h. Okay, so this is some function of n. And it looks kind of logarithmic, right? It crosses here in a particular spot. Now, the function that we care about is log n, and so this is the running time of our algorithm. The function that we kind of care about is log of n. And again, you know, I don't know exactly what this looks like, but I'm going to draw it like this. Okay, so that's the characterizing function that we care about. We don't really directly care about the relationship between f of n and g of n. As I said before, we've got this fudge factor that we can use, and this is what's really important. We've got this fudge factor that really just scales g of n. And this we call c times g of n. Okay, so it is effectively a way of boosting up your hypothetical running time, your asymptotic running time. Okay, so I think that this picture pretty well captures the inequality part, the less than or equal to part of that picture. And what I want to know from you now, what I want you to help me with is, where is k in this picture? Where's k? Can you see it? Do you see where k is? Yeah? Yeah, good. So it's here, And it's for all n greater than this spot. So there is this spot on the axis here that we refer to as k, right? So it's right about here. And there you go. That's a pictorial representation of that definition. Now, we could make this argument about AVL trees, but it would be ugly, and I don't want to do it. Okay? I feel petulant, I feel lazy, and I don't want to make this argument. It ends up being like, fraught with error, and I get the inequalities going the other direction. So I want to simplify my life, and your life too, and thus your life too. So here's what I'm going to do. I'm going to let you know now ahead of time. You know, I had to struggle with this originally, but now I know, and so now I'm passing on the word to you, that the argument about AVL trees is easier to make if you invert all these functions and make the argument about the inverted functions instead. So I have drawn that axis system in a color-coded way to denote the fact that we're going to take all of these functions and invert them, okay? And by invert, I really mean in the mathematical sense, right? I'm going to take F inverse of what we have here. Okay, so what on earth does this look like? Well, first of all, our functions are going to be in terms of h. Okay, and they're going to give us values that constitute a number of vertices. All right, and furthermore, what does the blue one look like? Oh boy, it looks like this, kind of, right? Is that what the blue one kind of looks like? So this function is F inverse of h. Yeah? Okay. And then what does g of n look like? Oh boy, it's closer to this. This one looks like this. We don't care so much. That's not the one we care about. And then there is, oh, sorry, this is inverse of h. And now there is this other function, the red one. I'm going to try and draw it. It looks like this. Now, instead of writing this as a c time, instead of inverting that function explicitly, I'm going to write it like this. I'm going to say there's a different constant, which is a function of the other one. Okay, it's like g inverse of it, I think, times g inverse of h. Okay. So inverting this one is a little bit different, but you can bring it down to a different constant times that. Now I'm also going to draw k on this picture. It's about right here, right? Here's the original k. I guess I should write it like that, kind of. That's kind of fun. That's supposed to be funny. And note that this could be considered to be a different k. Now, I have a question for you. I've now drawn a different picture, right? Like, this is a different picture than this one, but it has some similar characteristics. What I want to know from you is if I were to make the argument of, if I were to say, oh, this picture captures a definition, what definition does it capture? This is CS 173 brownie points, if you get this one. Do you know what picture that captures? Yeah? Yeah, this is exactly omega of h, actually. Omega of F inverse of h, right? Because look what we have. Instead of F of n less than or equal to c times g of n, on the right-hand side, we have the inverse function is greater than or equal to c prime times g inverse of h. So a constant times a function. So on the right-hand side, we're actually saying that F inverse of h is big omega of g inverse of h, of log of g inverse of, no, I don't need the log there, of g inverse of h, okay? That's the definition that is captured. And yet, all I did was invert the picture, right? Like I just drew the picture a different way. So here's what we're going to do. We're going to use that same reasoning and invert our argument, because it turns out if we look at the argument this way, that is as a lower bound on the height, it's a much simpler argument. So that's what we're going to do, okay? All right, so any questions about that? So let me read it clearly. An upper bound on the height of a tree, where the height means the running time of our algorithms. So an upper bound on the height for a tree of n nodes is the same as a lower bound on the number of nodes in a tree of height h. It's the same process, it's the same proof. And all we have to do to get the result that we want is to invert. Okay, so we're going to define n of h to be that lower bound. So n of h is defined to be the least number of nodes in a tree of height h. Oh, in an AVL tree. That's important. Okay, so it's the smallest number of nodes possible in an AVL tree of height h. Okay, so there it is. That's the description. We're going to kindly blindly follow the instructions here. I want to find a recurrence for n of h, and the smallest, and I'm going to do this for h greater than or equal to -1 here, okay? So what's the least number of nodes in a tree of height -1? Yeah, 0, right? Good. You got it? That's what we use -1 for. Just because we're not quite sure what we're talking about here, let's do n of 0 as well. What's the smallest number of nodes in a tree, in an AVL tree of height 0? 1, good, because that's, you know, a height 0 tree has 1 node. And just to see if you're awake, which is a valid concern here, what's the smallest number of nodes in a tree of height 1? In an AVL tree of height 1? 2 is correct. Make sure you all see that. Make sure you understand that 2 is the correct answer here, because this is a valid AVL tree. Okay? All right, so those are our base cases. I don't think we need to go on. Though, what is it for 3? N of 2, I mean. Oh. There? 4? Yeah? All right, in general, what is it? N of h is, I want you to write this recurrence. I would like for you to write the right-hand side of this general case of the recurrence, okay? And I'll give you a little hint. What you need to do is count the root together with the number of nodes, the least number of nodes you can put in each of the subtrees. Okay, and I'm going to walk around because I want to see this. Somebody asked me the other day if when I gave little puzzles for students to do, if they actually wrote them down. So I'm not looking for correctness here, I'm looking for participation. Good. Remember that it's the smallest one. So I mostly agree with that, but I think you can make it smaller. Okay, well, let's do what I said, which is count all the nodes. How many nodes in the root? How many nodes in the root of the tree? 1, good job. So the total number of nodes in a tree of height h is 1 for the root, plus what's the smallest number we can put in one of the subtrees? we must have a tree of height n of h minus 1. We must have a subtree of height n of h minus 1, right? Because otherwise the current one wouldn't be n of h, right? It wouldn't be h, have height h. Okay, how about the other subtree? Somebody raise their hand and have the conversation with me. What is it? Yeah? Very good. It's n of h minus 2, right? Notice in a regular binary search tree, this is 0. You don't have to put any at all in the other subtree. But in an AVL tree, you have to have its height differ from the sibling subtree by no more than 1. So in an AVL tree, you must be adding at least the smallest, at least n of h minus 2 nodes in the smaller of the two subtrees. Okay, fine. I've got another question for you. Tell me if you believe this. Do you believe that? Yeah. 10 is more than 9. A million is more than 999,999, right? The inequality simply says if you take one away, you go smaller. Okay? We took a piece of candy away. We know how to deal with this inequality. Now, what you might not have known was that it was safe for me to do so. That doing this doesn't hurt my argument. Okay? All right. So I'm going to do another thing. I also know that that sum is at least as big as 2 times n of what? What goes in that blank that I've left there? One or two? One or two? 1 or 2? That's right. That's right, right? Look, I've got this one, n of h minus 2, that's littler than this one. So 2 of these has to be smaller than 2 of these has to be smaller than one of those plus something bigger. Okay? So now 2 of n of h minus 2. Okay, you good? So I don't think I've said anything so far that's surprising, but what I think is surprising is the fact that it's okay for me to say these things, and that it's useful for me to say these things, right? Like you think we're lost. You think we have gone on a hike and we are lost. But I'll tell you that I have hiked this path before, and I know that actually this will be useful to us. And next time you see an argument like this, you'll go, oh yeah, okay, I can kind of guess where we're going with it, okay? All right, so now, to pull this together, remember that what I care about is a lower bound on the number of nodes. That is, I want to be able to bound my number of nodes from a function below. So it's okay if my function below is actually a lot smaller than the number of nodes that I've got. This is transitivity in action, okay? So here's my number of nodes, my real number of nodes. Here's my real recurrence that is the least number of nodes, okay? Here's my real recurrence here. And here, lower, is this bound that I have stated here. I need a lower bound on my number of nodes, right? I need a lower bound. It's okay if it's quite a bit lower. We've got a constant factor slush that we're allowed to have. And I happen to know, because I took this class before, a lot of times, that this is not too much slush, that this inequality, that letting it slide a bit will result in a conclusion that gives us big O of log n still. Okay, so what I want then, oh, that's what I did here. I simplified the recurrence. What I want is a solution to this recurrence. So what is this in general? So this is the simplified recurrence is n of h is at least as big as 2n of h minus 2, n of 0 is 1, n of negative 1 is 0. That's the whole recurrence. Okay? Now solve this recurrence. What do I mean by solve it? I mean guess a closed form. So I want n of h is at least, how do I solve this recurrence? Yeah, what's the closed form? So here's the observation. Every time your height increases by 2, you get an additional factor of 2, right? So this is going to be 2 to the something, and that exponent increases every other increase in height. So your closed form is that the number of nodes, the least number of nodes in a tree of height h is greater than or equal to 2 to the h over 2. And that's when h is greater than or equal to, oh, I don't know, 0. Does it work? Yeah. Make a negative 1 here. You want it to be negative 1. Does it still work? I don't think it works. It doesn't work at negative 1. Okay, so this is for all non-empty trees. Okay. It's really close, but not. Okay, any questions about all this? But this is okay. I don't really care what this is. I just need to know that this is the exists. There exists a constant. So it just needs to be somewhere. Okay. Let's see. So anytime anybody ever presents you with a closed form solution to a recurrence, you get cynical on the whole thing. And you begin to question, well, you can't just state that that's the closed form for a recurrence. You need to prove that it's true, especially in this case when we've got a lot of moving parts going on. So here's our theorem. An AVL tree of height h has at least 2 to the h over 2 nodes anytime h is greater than or equal to 0. Okay, so for any h greater than or equal to 0. Note, I could have chosen h greater than or equal to 5 if I wanted to. All right, well, it looks to me like this is a recursive, or an inductive proof. I'm going to start with the case that h is equal to 0. Okay, the base case where h is equal to 0. N of h is, n of 0 is 1, and that's given. And 2 to the 0 over 2 is 1, so the inequality holds. Okay? N is going to be our number of nodes, the true number of nodes. I mean, the minimum number of nodes. It's the same. It's a definition. Okay, case 2, and I'll ask you why we need this in just a minute, is for a tree of height 1. Does the inequality hold? Well, n of 1 is, what did we say it was? 2 is given. And 2 to the 1/2 is, root 2. And 2 is bigger than root 2, right? Phew. So the inequality holds. Okay. So our base cases are good. And now, for h greater than 1, we're going to look at the general case. All right. By an inductive hypothesis that says for any j less than h, n of j is greater than or equal to 2 to the j over 2, where n of j is, that recurrence. Then we do the following. So we know that n of h is greater than or equal to 2 times n of h minus 2. We showed before. I don't know why I wrote this. This is wrong. Okay. Okay? Well, how does this help us? What do we know about this? N of h is greater than or equal to 2 times. What do we know about n of h minus 2? What do we know about this? How do we know anything about it? What gives us a clue for that smaller instance of our recursive expression? Yes? From where? This is our recurrence formula, right? This is our recurrence formula, and my question is, do we know anything at all about this? No, we don't have to anymore. That one's gone. We don't care about that one anymore. The question is, I mean, so, like, maybe, but I'm going to tell you we don't need to. So that's not it. Good guess. That's not it. How do we know anything at all about smaller instances of the problem? Yeah? Exactly. That's what the inductive hypothesis is for. The inductive hypothesis is for us to take our recurrence and simply solve each of the smaller cases. That's why we have it. That's why we spell it out. So, in this case, I'm going to say, look, I know this recurrence. I know this recurrence. Okay? Yes, it's a recurrence. It has an inequality. It's still a recurrence. I know this recurrence is true. My inductive hypothesis gives me a different expression for that. It says that this whole thing then must be greater than or equal to 2 times. The application of the inductive hypothesis says this is 2 to the h minus 2 over 2, which is equal to 2 to the h. Good. 2 to the h over 2. You see that? And this is what we were trying to prove. Yay. Okay? Ah! Magic. But we're not quite done, because you look at it and you go, oh, well, the number of nodes is bigger than h over 2. Okay, whatever. Except look, our true number of nodes in an ABL tree, I'm going to use n for that because that's what we use on the graph, is greater than or equal to the minimum number of nodes in an ABL tree, which is how n of h is defined, which is greater than or equal to 2 to the h over 2, which we just proved, right? Now I'm going to get rid of, by transitivity, I know I can get rid of this central part. I don't have to worry about that part of it. And now I'm going to use high school algebra and invert this thing, okay? Because that's how we finish up our argument. That's how we did the last step on the very first slide. So I'm going to take log of both sides. Log of n is greater than or equal to h over 2, and then I'm going to multiply both sides by 2, and all of a sudden I have that the height is less than or equal to a constant times log n. Okay, so here, and this is true, this one was true for h greater than or equal to 0, so this one is true for n greater than or equal to 1. Now, these two things together are the very definition of big O, right? Let me give you some different words. H, proportional to my running time. Running time is less than or equal to, because I'm going left to right, right? Running time is less than or equal to a constant times log n for sufficiently large n. So running time is big O of log n. I can tell by your silence that you love this. Are there any questions? So this is good news. So even though we cannot prove that these AVL trees are as short as they could possibly be, they are certainly only a constant factor times as short as they could possibly be. And in fact, at worst, twice as tall as they might be. Okay, I'm going to flip the slide. You okay? Because this is going to be now the summary of AVL trees. All right, there are two balanced binary search tree structures that you're ever going to hear about in your life until you dive deeper into theory. And even so, most of them are modifications of one of these. Most sophisticated balanced binary search trees are modifications of these two classic ones. The red-black tree is slightly different. The guarantee on its height is twice log of n, and you're going to do a constant number of rotations. I think it's up to 2. For insert, yes. Also for remove, and maybe even for find. Okay, so red-black trees behave differently in terms of the amount of work you have to do to maintain the balance of the structure. Only slightly, there's just different algorithm. AVL trees, on the other hand, have height that is guaranteed to be 1.44 times log base 2 of n. Wait a second. Is that what we just proved? No. What did we prove? Oh no. What's the difference? Where might a smaller number have come from? Where might a smaller number have come from? Yeah, in 173, I don't know, probably, and there's some discrete math somewhere, you would have learned, you may have learned, maybe you learn it later, I don't even know, how to solve recurrences that look like the original one explicitly. It involves finding a characteristic equation. I believe you have to find the roots of a degree 4 polynomial in this case. We don't do it here because we have this nice way of simplifying the problem. But if you had explicitly solved the recurrence, you would have found a bound which is tighter, a better bound. Okay, but we didn't need it. We just want big O, so I'm happy with big O. All right, and then the further clarification on AVL trees is that you might have to rotate this many times upon a remove. That is, you might have to rotate at every level of the tree upon a remove. On a find, you have 0 rotation. And on insert, you have 1. Okay, so insert, remove, and find are always log n. Yay, that's good news. It's an improvement over what structures did we use for dictionaries before? What structures could we have used? Plain old binary search trees, but what else could we have used for the dictionary ADT? Linked list, yes, and we could have used an array. We might have been able to use a stack and a queue, but oh my gosh, that would have been nutso, because we would have had to I don't want to find a key in a stack. I don't know what I would do. It's like finding a grape candy in a Pez dispenser and having to put things back. Not a good idea. Okay. MP6 is going to ask you to use a balanced tree that's not quite binary search-ish to find nearest neighbor. In 374, you're going to be doing range finding algorithms. But there are some negative things too, and I guess we'll start there next time. Oh, I didn't notice. It's okay. I fell asleep too.